Hi, the objective of this video is to show you how to find and use zeros of polynomial functions as sketching aids. So let's first review what a zero of a function is. The zero of a function is a value of x that makes the function zero. So real important here is that the zero is the input that makes the output zero. Okay, so we're talking about what value makes y equal to 0. And graphically, the zeros are the x-intercepts of the graph. And I've shown you a few here. So like on this particular graph, there are 3 zeros, specifically at 2, 4, and what is that, -5. The other function we have graphed has 4 zeros at 2, 4, -2, and -5. A real important thing when dealing with polynomial functions is that the degree tells you the maximum number of zeros that you can have. Well, let me back that up. The degree tells you the number of zeros that you can have. Now the reason why I said maximum is because it counts a zero that repeats itself, and it also counts within that complex zeros. So for the real zeros, the real valued zeros, there can be at most n of them if n is the degree of the polynomial. Also, there can be at most n minus 1 turning points. So if the degree of the polynomial is 3, which this is an example of a cubic function here, then there can be at most 1, 2 turning points. The example that I graphed here is a 4th degree polynomial, and so that means that there can be at most 4 minus 1 or 3 turning points. Okay. Now the turning points are where you get into maximum and minimum points, and that was covered in college algebra. We're going to get into that a little bit in the next section as well, but right now don't focus too much on those because we're going to just kind of get a rough sketch of what the graph looks like. So some fundamental things that you need to relate together for zeros of a polynomial function. If f is a polynomial function and a is a real number, then the following statements are equivalent. So if we know that x equals a is a zero of the function, that means that x equals a is the solution of the equation f of x equals 0, because that's how we find the zeros, right? We have to set y equal to 0 and solve for x. Also, that means that x minus a is a factor of the polynomial function. And lastly, if x is a 0, if x equals a is a 0, then the point a0 is the x-intercept of the graph. So things that all mean the same thing, one implies the other. So very important to kind of link all of those concepts together. So let's look at some examples. We want to find the zeros, determine the multiplicity, and I'll define that as we go through it, and then I have another slide that will tell you specifically what that is. And then we're going to verify on a graphing calculator. So f of x equals 49 minus x squared. So if I want to find the zeros, I've got to set the expression 49 minus x squared equal to 0. Well, that is the difference of 2 squares, so we can factor that to be 7 plus x times 7 minus x. So therefore we find that x equals -7 and x equals 7 are our zeros. Now I'll show you the graphing calculator in a minute, but the multiplicity means how many times does a factor appear that caused the solution. So like 7 plus x was raised to the power of 1. Therefore, x equals -7 is a single solution. It doesn't repeat itself at all. So the multiplicity really gets into how many times is that 0 repeated, and that is indicated by the power on the factor it came from. Now, what about x to the fourth minus x cubed minus 20x squared is our polynomial function? Well, to find zeros, I'm going to set that function equal to 0. So notice that there's a common factor of what? Yeah, x squared. So if we take out an x squared, that leaves us x squared minus x minus 20. And we can factor that. The factors of 20 whose difference is 1 would be 5 and 4, so we need x minus 5 and x plus 4. Okay, so when we set those factors to 0, we would get x squared is equal to 0, x minus 5 equals 0, and x plus 4 equals 0. So x squared equals 0 really tells us that x would be plus or minus the square root of 0, so that would be plus or minus 0. So this is called a root or a 0 of multiplicity 2 because it really repeats itself, though we don't include it twice in like a solution or anything. We also have x equals 5 and x equals negative 4. And I'll show you what happens when we have a multiplicity other than 1 when we look at the graph. Okay, and now we'll look at g of t, which is t to the fifth minus 6t cubed plus 9t. So if we set that equal to 0 to find our zeros, we have a common factor of t. So now we need to find the factors of 9 whose sum is 6, which would be 3 and 3. So that would be t squared minus 3 times t squared minus 3, so we can just put that as t squared minus 3 squared is equal to 0. So now we need to think about the factorization of this, so that means that t is equal to 0, or t squared minus 3 squared is equal to 0. Now we can take the square off by taking the square root, so we would get t squared minus 3 is equal to plus or minus 0. T squared is equal to 3, so t would be equal to plus or minus the square root of 3. Okay. So let's look at what happens to those roots, because there's a power of 2 there, so there's really appearing twice. So these are roots of multiplicity 2 as well. So let me show you the calculator and we'll figure out what happens to the graph when there's a multiplicity other than 1, as I said before. Okay, so let's take a look at the graphing calculator. So I've pulled it up on my screen, and let's look at the graph of 49 minus x squared. So I go to my equation editor and enter 49 minus x squared. We know this is a quadratic, so the graph is a parabola, and there are 2 zeros of the graph at negative 7 and 7. So understand that those zeros again correspond to the x-intercepts of the graph. And one other thing to note is that at negative 7 and 7, the graph crossed through the x-axis at those points. Now let's enter the next function, which is x to the fourth minus x cubed minus 20x squared. Okay, and I'm going to press graph. Now I could enlarge my window if I wanted to see a complete graph of this. Let's see, if I take it down to like negative 200, let me extend my y-min to negative 200. Okay, it's a little bit better picture. So understand what we talked about. Algebraically, we found 3 distinct zeros. We found 0, 5, and negative 4. Well, notice that at negative 5 and 5 and negative 4, our graph crosses through the x-axis at those points. But at 0, which was a root of multiplicity 2, it does what? Yeah, it goes down. In other words, it just touches the x-axis and comes back down. So when we have a multiplicity that's even, 2, 4, 6, whatever, the graph is actually just going to touch the x-axis at that point. If the multiplicity is odd, like 1, 3, 5, then the graph will go through at that point. Okay? Now, let's look at the last function and just see if that corresponds to what we just talked about. So we have t to the 5th, or we'll input x to the 5th, minus 6x to the 3rd, plus 9x. Okay. And we press graph. And let me adjust my window. Let's go back to the standard window just to see if that's going to do it for us. Okay. And it does. So notice what we found here. The plus or minus square root of 3 were both of multiplicity 2. And do you see what the graph does there? At negative square root of 3 and at positive square root of 3, it just touches the graph there. But what happens at the other root, which is 0? Yeah, it goes through it. So pretty interesting. So the multiplicity can tell us how the graph is going to look at that 0. So I actually have that information detailed for you on this next slide. So here's some information you need to know. Repeated zeros. If x minus a to the k, where k is greater than 1, is a factor of the polynomial function f, then x equals a is a 0 of multiplicity k. If k is odd, the graph crosses the x-axis at that point. So if this is a and k is odd, it's going to go through the x-axis. Now it could certainly come down through it, but it's going to cross it. If k is even, the graph touches the x-axis at a. So that's where it's going to go down to it, touch it, and come back up. Okay? So the last thing in this objective that I want to do, and we're going to actually put all this together in the next objective, but here is to find a polynomial function with the given zeros. So this is to make sure that you understand what it means to be a 0 and how that relates to the function. So the key thing here for you to think about is this, that if x equals a is a 0, then x minus a is a factor. So knowing the zeros tells us how the factorization of the graph or the function is. So if I have the zeros are 0, 2, and 5, then that means that x minus 0, x minus 2, and x minus 5 have to be factors of the function f. So f of x would have to be, in this case, x times x minus 2 times x minus 5. Now understand there are many, many, many functions that would satisfy this criteria, because I can make those zeros of multiplicity k. It doesn't really matter what the multiplicity is, because that factor still results in that same 0. I could also put a coefficient in front if I wanted on the x. So let's just, for fun's sake, say we want this to be x times x minus 2 squared times x minus 5 to the 3rd. Now you can certainly leave them as all linear factors, it doesn't matter. Now the next one is to find a polynomial function with these zeros. So with these zeros, that's going to tell us that x minus a negative 2, x minus a negative 1, x minus 0, x minus 1, and x minus 2 all have to be factors. So we could have f of x would be then, what, x plus 2 times x plus 1 times x, I should have put that out in front here, times x minus 1 times x minus 2. Let Let me put in my x a little bit clearer there. Okay. I still didn't get it right. Sorry about that. Do over, huh? Now, if you wanted, you can multiply these out. You certainly don't have to do that. But you might recall that x minus 2 times x plus 2 is x squared minus 4, and x minus 1 times x plus 1 is x squared minus 1, so you could write it in that form if you wanted. Here again, you could have different multiplicities on those factors. You could have a coefficient in front of the x, but those would still result in the same zeros for that function. Now, for the next one, we are given specifically what multiplicity to use. So if we have negative 5 is a 0 with multiplicity of 3, and 0 is a 0 with multiplicity 2, that means our function is going to be something of the form. We'll do the 0 one first, because we would have x minus 0, which is just x with the power of 2, and then x minus negative 5, which would become x plus 5, but now with the power of 3. And here again, I could put some coefficient of the x squared if I wanted. Okay, so in the next objective, we're going to actually see how all this comes together using the leading coefficient test, the zeros, to actually graph a polynomial function.